Dennis, please educate us.
Thank you very much.
Thank you.
And thanks for having me. It's a great pleasure to be here, really. So my name is Denis, and I work at Intel. We do C++ compiler development, and today I want to talk about performance analysis and tuning on modern CPUs. That's what we're doing on a daily basis. Okay. So they say performance is king, right? It was true a decade ago, and it certainly is true now. With the more and more amount of data that the world generates every day, you actually need more and more compute power to process. And actually, it used to be the case that some software vendors relied, so they actually did not spend human resources on trying to optimize their code, but instead they relied on hardware to provide this performance, right? Speed ups. Now, when it's no longer the case that each hardware generation actually provides 2x performance increase, we must start paying attention at how our code actually runs. Okay? And if you look at the blue dots here, you can clearly spot that the trend of single-thread performance or a single core performance is like definitely slowing down. So and I believe that the value of careful performance analysis will only increase in upcoming years. So modern cores are getting, modern CPUs are getting more and more cores each year. Well, I mean, at the beginning of 2020, you can go out there and buy high-end server CPU which will have like more than 100 cores in it. Now, it will be expensive though. Actually, it may sound impressive, but it doesn't mean that we don't have to care about performance anymore, right? Because your application might not benefit if you will just throw more cores at it, right? So if you look at the typical general purpose application, it doesn't scale linearly as we want it, right? With the amount of cores we added. So, and what do I mean by performance analysis? I actually see a lot of people rely on their intuition when they make code improvements in their code. But unfortunately, it ends up with random fixes here and there without really making any real positive impact on performance. So I believe that performance analysis, I believe that the code changes, the changes in your code that you do with regards to performance should be driven by careful performance analysis, not your intuition. Okay, your intuition is usually wrong. Remember always to measure. Now, it actually might be tempting to ask, why hardware doesn't solve all our problems. And indeed, the CPUs nowadays are extremely powerful, and they're extremely great at crunching numbers. But they are helpless if you throw bad code at them, right? They will just silently execute whatever you told them, and will not make any attempt on, somehow make things better. Then you might ask why compilers doesn't solve all our problems. And indeed, compilers are also smart. And they are extremely great at eliminating unnecessary work. But when it comes to making more complicated decisions with regard to performance, like for example, function inlining or loop unrolling, loop vectorization, it usually actually tends. They usually rely on their cost models and a whole bunch of heuristics, which are, of course, not optimal for every case. So compilers are also subject to making suboptimal decisions. So here is the agenda for today's talk. We'll actually briefly jump through the first two bullets, which are how to conduct fair experiments and how to process and compare results. I promise we'll go through real quick through first two bullets because I believe most of you will not have to worry about those things on a daily basis. But still, I believe that this is sort of important, and I want to spend just a few slides on it. Then we'll talk about what is profiling and how it works. Then we'll talk about how your code looks like from the CPU perspective, and how to find inefficiencies there. And in the end, I have some examples of code tuning that are specifically for sort of intended for targeting CPU. So as a motivational example for today's talk, suppose we have a function that we want to benchmark. Now, well, imagine that we measured it, and we measured the throughput, and we have some number, right? So, but now we inserted just some function that does not affect really the benchmark itself, but it just happens to be there in the binary. It just stay there, and suddenly you have 15% speed up. But actually, so don't get me wrong. I'm not advocating here for inserting dummy functions all over your code, okay? But assembly code is exactly the same in both cases. Okay, it's just what is different is just the offset of the function at which they are placed into binaries. Okay, so this is like a funny hardware effect. To make it even more funny, I did 2 more experiments, and I aligned my function at 32 bytes boundary offset, and I have plus 32% speed up. Then I aligned the basic block, all the basic blocks inside this function at 32 bytes boundary, and I have even more stunning 48% speed up. Now, I was writing C++ I was writing conventional C++ for many years, and I thought that compiler writers are like magicians, cowards, wizards, or whatever. Now when I'm actually doing that myself, I tend to think that this is the real magic. Because, yeah. No, but seriously, if you want to know more details about why it happens with, I actually have a blog post that I wrote, well, almost 2 years ago. Now, because the explanation for this will involve a fair amount of microarchitectural details, which I want to avoid for now. But the bottom line here is that 48% is just huge for us. We will all get the promotions if we can deliver that amount of speed up across all the workloads in the world. Okay, we probably will get promotions even if we'll deliver 15%. But anyway, so the motivation here is that we don't want to miss those opportunities. We want to know about those hardware effects, and we want to take advantage of them. So, so let's jump into the first topic: is how to conduct fair experiments. Actually, initially I had a bunch of boring slides, which I decided to remove, and just give you the raw ideas and thoughts. So the thing here is that modern environments are really noisy. There is a lot of non-determinism in modern systems. There are a lot of features that are supposed to improve performance, but none of them have deterministic behavior. Like take dynamic frequency scaling, for example. So this is the feature that the CPU has. It is able to scale its frequency up to the extent of the terminal package allows it to do. Okay. So, but it is non-deterministic, meaning that we never know when it will kick in. We never know. It's hard to predict its behavior, but it certainly can affect the final scores and measurements. So ideally, we want when we want consistent results, consistent measurements. We want to disable all this non-determinism. And actually, and the big companies like Intel, for example, have a dedicated pool of machines which are specifically tuned for performance measurements, where minimal background processes are running. No one is allowed to log into those machines, well, of course, except the CI, which submits sort of the nightly tasks, the nightly benchmarks to those systems. And minimal non-determinism. Again, more details in my blog. And there's actually a Python tool that is supposed to set up your environment properly. This is for Linux, and macOS is partially supported. So this is the tool for setting up your environment for benchmarking. So it tries to do everything what we just told, well, with regard to non-deterministic features.
But there are system settings that cannot be touched by programs running at user level, such as any Python code. And there are system settings that require that have to be adjusted or properly configured in the BIOS. So
yeah,
that probably does something, but I don't think it covers the entire repertoire of settings that need to be set correctly to get high accuracy, reliable, consistent results.
right. Yep. So the comment was, or rather an observation was that that there are certain parameters that you cannot control, right?
They can all be controlled, but they cannot be all controlled from user space. So, just to give you an example,
right,
to disable C states in Linux, you actually have to recompile the kernel because there is a boot flag that says C state max C state 0, and the kernel ignores that, and you have to know how to fix the kernel to not ignore that.
Right. So that's why you want to have the pool of dedicated machines that are specifically have all those C states
Absolutely.
configured properly.
You have to have
proper
a lab.
BIOS settings and all this. Yeah.
You have to have a stable, controlled environment where you control not just the machines, but the airflow, the temperature, the humidity.
Yeah. Yeah. I mean, if you want to go that far, then yes.
You have to go that far.
Sometimes you have to.
On modern machines, you have to go that far. I have empirical evidence to back that up.
Well, I think that sometimes actually this is more of a business decision sometimes. So the question is how accurate you want your measurements to be, right? So sometimes you can afford having having a little bit of deviation in your measurements, but do not care about all the possible things that can happen. That makes sense.
Okay, I'll take your word for that.
All right. Let's move on. So the second thing is, actually, how to process measurements and compare results. So the thing here is that suppose we make some code change and we want to know whether we improve performance or not, and if we improve, by how much. So what do? We take the baseline, which is version A. We make the change in our code. We recompile the code, and we have the modified binary, which is version V. We run the version B. Now, we don't run it just once, right? We take multiple measurements. So we have a measurement set for baseline, measurement set for our modified version. Now the question is, which is faster? And usually we take some single metric. We take some representative number from both sets, and we take the ratio. This is how we know which one is better, right? Now again, I had a bunch of slides which I removed, so just give you the ideas. So if you actually if you talk to any data scientist, he or she will immediately tell you that picking single metric is just, well, it's not wrong, but it's not perfect. So but for automation purposes, we need to track it, right? We need to pick the single number from both measurements just to being able to compare them. So the second advice, if possible, make many benchmark iterations. Now this may sound obvious, but actually there are situations when you cannot afford running your benchmark many times. Like some of the spec benchmarks run for 10 minutes, so it will take you just 1 hour to produce just 3 samples. Okay, because 3 samples for the baseline, 3 samples for the modified version, like they will take 1 hour in total. So if you cannot afford a rich collection of samples, you should be careful with taking means or geo-means. Why? Because they can be spoiled by outliers. So in this case, you can actually consider taking minimum or medians. Again, if you want to know more details, I have a lot of charts here in my blog. And if you actually want to be on a safe side, like for example, you're presenting your results to the management, you can actually plot the distributions and let them drive their own conclusions from those plots.
But that may actually not be the safest side if you let the readers drive their own conclusions.
Yeah, well, but at least you will be not the one to blame. I mean, yeah, anyway. All right.
A question.
Yeah.
Why not just, if you're saying my code has been changed, why not just always use the minimum? Because isn't it going to be slower because of everything else in the system?
Yeah, I mean that's actually a good point. And you know, I really want you to encourage you to go and actually have exact explanation why minimum can be also bad. Because you know, there could be a situation that 2 versions have the same minimum value just by accident. But if you look at the distribution, the whole distribution, one distribution, like the mode of the distribution will be wider in some of the cases, and you will not catch that if you will take just the minimum. Okay. All right, let's move on. So the next topic is what is profiling and how it's working. So, you know, the time is the ultimate metric for judging about performance, right? But how do we know why really like for example, you made some change and it seems harmless from the first sight, but and you do not understand why really the code gets slower. So that's why you need really to do performance analysis. And historically, there are 3 main approaches to performance analysis: code instrumentation, profiling, and tracing. Now, unfortunately, I don't have time to talk today about tracing, but actually there are some revolutionary technologies being developed for tracing specifically, and Intel has the feature called Intel Processor Trace, which allows you to trace every, and I mean every, assembly instruction in your code. Okay, this is really powerful. Again, if you want to know more details, please check out the blog. Now, code instrumentation. So who ever inserted the printf statements just to count the number of times the function gets called? Right. No, I mean I did that myself a number of times, but you know I actually, so what I see is that not much people nowadays are doing this. It's more of a now this process is actually now automated. So for example, the compilers are using this technique for doing automatic instrumentation of your code and collect some interesting statistics from it. This is for example how profile guided optimization works. Yeah. So now actually let's move on to profiling. So how many of you ever profiled the application? All right. So then this picture should be familiar to you, right? The main purpose of profiling is to identify the hotspots, right, in your code. So what do you think is the easiest profiler?
Your wrist watch. Press enter and then you look at your clock.
Yeah.
GDB.
Oh, right. That's an answer.
Basically, if I may answer your question, there is only one profiler in the industry that is worth using. That is VQ. Everything else is garbage, and I can prove that. It has been verified many times. VTune is not perfect, and one can do better, but to do better than VTune, you'd have to write your own profiler.
Well, okay. So actually, the easiest profiler is debugger. I mean, it may be funny, but actually, if you take your application and you run it under debugger and you stop it after each second, and if you will do this a lot of times, you will get the collection of the places where you stopped. Okay. If you then build a histogram from this collection, you will actually can see where you stopped the most, and this will be a hotspot. I mean, it is of course oversimplified version, but it is not that far off of how modern profilers work. So modern profilers are capable of collecting thousands of samples per second. And then, so consequently, the profiling is based on interrupts. So in order to explain interrupts, I actually need to explain a little bit of performance counters. Don't worry, it will be super quick. Now, if you're anywhere like from, if you just graduated the computer architecture course, this will be your CPU mental model. We have caches, we have branch predictor, we have the execution pipeline with multiple stages in it, and then we have a clock, which sort of sends pulses to all the units and makes everything move to the next stage, right? If we add a little bit of silicon and we wire it up to the clock, we can count cycles. With every pulse that the clock generator sends, we'll increment our counter by 1. This is how we count cycles. I mean, it is super easy, but well, I mean, how about counting more? So, if we add more wires to the system and connect our counter to multiple units, suddenly we can count many different events. Like for example, we can snoop into caches and collect cache misses. We can snoop into branch predictor and we can collect branch mispredictions. We can snoop into pipeline and collect the amount of retired instructions and number of loads and so on. And notice I also have a configuration register because now I need a way to tell which event I want to count. Right? That makes sense? So now there are two main applications to performance counters. The first is counting events, and this is like a super trivial way to use it. But so what we do, we set the counter to 0. So actually not we do, but what typical profiling tool will do. It will set the counter to 0. It will configure the event that it wants to count. It will enable the counting, and it will let the benchmark go. In the end, we just disable the counting and read the value from the counter, and that's it. This is actually how perfstat is working. We just count the absolute number of certain events that happened while our benchmark was running, and those are absolute values. So. And you know, sometimes it can be really useful for comparing those absolute numbers. For example, if you have the baseline and modified version, you can clearly see, you know, the difference. It might provide you some insights. Then the second application is sampling. Well, it's the same as profiling. It's just another word for it. So the purpose of profiling is identifying hotspots. So what the profiling tool will do, it will set the counter to count cycles and initialize it with some n. I will actually talk later about what this n means. Then it will enable the counting and wait until the counter overflows. Now why is that so? Because remember, we count cycles. Our counter will be incremented after each cycle, right? So eventually it will overflow. And when it will overflow, hardware will actually raise an interrupt. It's called PMI, Performance Monitoring Interrupt. And then the tool will just let the benchmark goes. So, of course, our counter overflowed, and the hardware raised an interrupt inside. So the performance analysis tool, the profiler, catch this interrupt, and inside the interrupt service routine, what we do? We disable the counting. We capture the instruction pointer. This is the most valuable part. We captured the place where we stopped. Okay. After which instruction our counter overflowed and it triggered an interrupt. Make sense? And then we reset the counter again to this number n, and we let it go again until it overflowed again. And then how we build a lot of, if we then will catch enough samples, we'll build a rich collection. So what is this number n? If we want to have an interrupt after each million of cycles, then we set this n will be minus 1 million, okay? Because after million cycles, it will overflow, right? Remember the counter is unsigned, so setting it to minus million, it means that it will overflow after 1 million.
You said the counter was unsigned, and now you're saying that when it overflows, it would be a negative number?
No, it won't be. But what I mean is that you set it to minus million, okay? Sort of, you can count it as maximum.
How can you set an n
maximum
sign?
minus.
Modulo 2 power n.
If the counter is unsigned, you can't set it to a negative number.
I mean, okay,
overflow
you
it.
set it to maximum minus 1 million.
Yes.
That makes
Alright.
sense? Alright, so, and this is actually what perf record is doing. You can see that it collected 400,000 events, so 400,000 samples, and based on that, we build the histogram of our hotspots. Alright. Any questions to this point?
So the best way to visualize this will be a flame graph, right?
Yeah. Yeah.
Can you repeat the question?
Oh, yes, sir. So the best way to visualize this is to build a flame graph.
How you count the effect of interrupts? Because it disrupts pipeline, basically, and cache. So
Yes.
the measurement itself, it's Heisenberg theorem.
Yes. So yes, you should not combine your measurements and the profiling in one run of the benchmark. Yes. You should do it separately.
So you can also set this counter to the instructions retired or the branches taken counter as well, and then once it overflows, you can get an interrupt.
Yes, you can do this absolutely. Yes.
But are there real applications to it, or have you seen that in practice people doing it for some, like, I mean, you can always do a 1 millisecond interrupt, which is setting the cycles, but you can also do the instructions retired. But is there would somebody do it?
Yeah. So the question is there a use case to sample not on cycles but sample on any other event? And the answer is of course yes. So, for example, and actually I will have examples later, but just to quickly answer your question, if you want to know where, for example, what is the load that misses in caches the most? This way, to answer this question, you can sample on the different counter, not on cycles, but for example on L3 cache misses. This way you will build a histogram that will tell you the hottest, that will tell you the loads that contribute to a bigger number, to the biggest number of cache misses in your program. That make sense?
Yeah.
But why would you want to measure this? In the end, all you need is to speak to your program, right? And that's what cycle counter is for.
Well, right. This is if you want to know the hotspots. But if you want to know if you okay, let me just go later. I have examples for when it makes sense to sample on different events. Okay. So now let's talk about how your code looks like from the CPU perspective and how to find the bottlenecks. So, you know, in most of the cases, actually, the profile, knowing the hotspots, will be already a big deal. And, you know, sometimes it will be all that you need, really. Because, for example, if you have a major performance issue, it's probably not the best time to go to the CPU level. You must be fixing the high-level issue first, okay? So, for example, if you profile your code and you see that some function is hot, but it shouldn't be, then it's probably something wrong, like with how you perceive your program. Simple example might be if you profile your code and you see your sorting routine is hot, but it shouldn't be, and you know, and you look at the implementation and you see bubble sort, well, probably you should be fixing and choosing the better sorting algorithm, for example. Then, second advice is, like you avoid premature optimizations, you also should be avoiding premature microarchitecture optimizations. So, the example might be, if your software is not feature complete, then it's probably not the best time to think about the cache misses and branch mispredictions, etc. Now, and I actually find this list of high-level optimization tips pretty much compelling. We'll just briefly go through it. So, avoid interpreted languages in managed environments. Use better algorithms and data structures. Tune compiler options. Parallelize computations. Use asynchronous I/O and buy better hardware. That's just high-level tips. Now, if none of that helps, if none of that works, and you still need to squeeze more performance from your code, this is what you should be doing. And actually, I love this process just so much. So this is the top-down microarchitecture analysis. It was originally developed at Intel, and now AMD is actually also catching up with this. So this analysis is quite formal and robust enough, and it's sort of and the main advantage of it is that you can have absolutely zero knowledge about performance counters and about microarchitecture and still implement sound microarchitecture optimizations in your code. Now, this process works by characterizing your workload in one of the four main buckets. Those buckets are retiring, bad speculation, front-end bound, and back-end bound. Actually, later I have more examples. So, but the idea is that this is the top-down. So you're drilling down until you get to the real root cause. Okay. So, for example, on first iteration, you identified that your program is backend bound. Then actually the program will automatically do this. So the analysis will automatically pick the next set of counters and will calculate those two metrics and decide where is the bottleneck. Is it in core bound or your application is memory bound? And so this is how you drill down until you get like, oh, for example, my application is goes all the way down to the main memory, so it misses in all levels of caches. And the tool automatically does this for you. So originally it was implemented in Vitium in general exploration analysis. So on this slide you can see, and you can think about it as if 41% of the time was wasted due to incorrectly predicted branches. Okay. So now you first know where's the bottleneck, and second, you actually know what is your headroom for improvement, right? Because actually, so the retiring bucket is usually where you want to be. Okay, 100% is usually mean the good thing, although there are exceptions. So in this case, we can see that ideally we have probably like around 70% headroom. We can still improve. I don't mean that it will be hard. It will probably will be not so easy to do, and 70% retiring is already pretty much good. And actually, this is the real case. This is the benchmark from LLVM test suite 7Z, widely used out there. Now, yeah. So if you actually click, so again, the next good thing about this is if you click on branch mispredict, it will go into the more detailed view, and it will tell you what functions contribute the most to those number of branch mispredictions. If you then click on the function, it will actually get you to the source level view, and you will know exactly what is the line of code that sort of triggers or generates a lot of branch mispredictions. So knowing the issue, now you can actually now you can make corresponding decisions. So and actually, so the same process is if you don't have the access to Vitium, the same process implemented in Top-Level and Perf. And actually, I tend to use this more often than using Vitium, because Perf is installed on literally every Linux distribution that I use, and Top-Level is just a Python script. So it is exactly the same process. I will not now go into this. You can go and check it yourself on my blog again. But so actually, go into your question. So this is the case where you want to sample on something different than cycles. So this is how I sample on less level cache misses, and I know where are my cache misses, in which function, and if I will then drill to the source level, I will get to exactly the line of code which misses in cache, in less level cache. All right. So now actually, so the final topic for today is some examples of code tuning of real-world cases that you might encounter. And the first one is inline functions with hot prolog epilogue. So whenever you see a function which has the hot prolog and epilogue, it's probably the best candidate for inlining. Like in this example, the prologue and epilogue together take 50% of the time of the whole function. Now, those 50% are actually can be considered as overhead, which we want to eliminate. If we inline this function, there will be no prologue and epilogue, right? It will disappear. Now, one approach to inline the function is using the function attribute. Yeah. Again, this is example from the real code, from the real workload. Now, unrolling vectorization compiler things. Actually, so by the way, who ever used compiler optimization reports? Who know that they are now supported by Compiler Explorer?
Oh.
Yeah. So now you actually can go to Compiler Explorer. Well, it's there for a while, but you can go there and click on particular line of code, and in the separate window it will show you what optimizations were done on this line of code, which is pretty useful in some cases. So in this case, suppose I have a loop, and the client compiler told me that the loop was not vectorized due to the cost model. So compiler decided that it's not beneficial to vectorize my code. Well, what if compiler is wrong? So And the one way to test this is actually to use pragmas. There are pragmas for vectorization and unrolling. We can specify whether we want to unroll, vectorize, if you want to unroll by how much, and so on. So by telling this, you are telling the compiler essentially something along the lines of if it's legal to vectorize the loop, please just don't look into your cross models, into your cross models, and just vectorize. And you know, unrolling and vectorization can contribute to your performance a lot. So this is probably again where you want to look really. So then inserting likely comparisons. If you have a hot code and there is a function that does some, for example, error checking, it is called. In this case, you actually might want to tell the compiler that this condition is unlikely to be true, and compiler can reorganize the code to make it more efficient. In particular, so in initial case here, what we actually have a hot code, then we test the condition, and we jump if it's false. Okay. If it's true, we go to the call function, which is usually inline. Okay, if it's small enough, compiler will aggressively inline it, and you know, if we do the thing here, we actually maintain the false through inside the hot pass, which will essentially convert the taken branch here. This is the taken branch on a critical pass. We convert it into not taken branch. And fundamentally, not taken branch is cheaper than the taken branch, both in terms of throughput and latency on modern CPUs. Then this is the first case why it's better. Then the second case is that keeping the false through in your hot code actually better utilizes your instruction cache. Again, real world example where the improvement was something like 1.5%. You can do the same with switches. If you know that so in this case, there is a for loop, and inside the for loop there is a big switch that handles different instructions. If you know that one instruction is hotter than the other, so you execute, for example, additions more frequently than all the others, then you can tell the compiler using built-in expect, and the compiler will reorganize the code a little bit differently. It will actually extract all the code that is associated to handling addition instruction, and it will process this add instruction before entering the switch. Okay. Yeah. Again, if you want to know more explanation, I have a link here. Oh yeah. Then the case so how to find branch mispredictions? Well, one way to do this is to eliminate the branch itself. So suppose we have this code and this branch has high misprediction rate. What do I mean by high misprediction rate? If you have 90% of outcomes as true, for example, for this condition, then it will be predicted really well. CPU is like great at predicting such rate of true or false outcomes. If you have 50% true or false, well, in this case it depends. If you have a true, false, true, false, true, false, true, false, then the CPU will easily catch this pattern and will predict it 100% correctly. But if the outcome of your branch is like truly random, like you flip the coin, in this case the CPU will struggle with predicting it, and what you can try is actually you can sort of not force, but you want to suggest the compiler to use the cmove instruction. So, well, what is the cmove? Cmove, the conditional move instruction, is supported on on almost, I think, every CPU out there. But the important thing here is, so now actually what we are doing, we are computing both x1 and y1 sort of speculatively or sort of unconditionally, okay? And then we just select the result. So this is what CMove is doing. So we are emulating the CMove instruction in our code, but keep in mind that now we are doing twice more work as we've done before, right? But the cost of the branch misprediction is usually around 15 to 20 cycles on a modern CPU, because what CPU is actually doing when it encounters that the CPU has chosen the wrong path, it actually flushes the whole pipeline and starts like filling it again. So it's really expensive operation. But if your computation will be sort of a lower than this penalty, then you might want to actually be doing more work, and it will be it will end up being faster. Now I have a real world example. Actually, this was this 7-zip benchmark. Remember the slide with Vithium where it were 41% misprediction rate. So with this trick, I was able to improve the 7-zip benchmark by 9%. All right. Now, and I think the last example here is the memory prefetching. So if you have a loop and you have a load that misses in L3 cache a lot, what you might do is you might want to insert the prefetch instruction ahead of time, so that by the time when you really need the load value, it already will be in the cache. Okay, but make sure you insert the prefetch ahead of time, and so there will be enough window, and the prefetcher will be able to pull really the memory location into the cache, so that by the time you really need it, it will be in the cache. All right, now takeaways. Configure environment properly. Process result carefully. Remember, taking mean and geomean is not always the best choice. Know how you can identify the bottlenecks and headrooms of your application. Start all-level tuning only when all the major performance problems are fixed, and know the typical recipes for fixing inefficiencies. If you like it, I actually have more on my blog. I have a set of articles about advanced TPU features like last branch record, precise event-based sampling, and Intel processor traces. I also wrote a series articles about multi-threaded applications, like how to find expensive logs and how to detect fault sharing, and I have a lot more tuning examples. And some of my earlier articles are about CPU microarchitecture. And be sure to subscribe. Oh yeah, and you can find me on Twitter using this handle. And thanks for your attention.
Can you recommend an optimal kind of layout of the predictive branches, stuff like that? What from your own experience? Because I didn't catch it all. I mean, you took those were things, but kind of don't have a general way. Still get it.
I see. Actually, in general case, conveyor and jump will be faster in most of the cases. Only in the cases when you really see in the profile, right? So, if, for example, in this top-down methodology analysis, if it showed you that the number of branch mispredictions is high and the time that is wasted due to those mispredictions is high, only then you can find the exact branch that contributes to those branch mispredictions, and then you can try to fix it. Okay, but again,
This do trial and error. Don't have any optimal pattern.
optimal pattern. Yeah, I mean, and there is no optimal pattern. Like it depends on how well the branch can be predicted by the CPU, and and you never know it in advance, right? So the recipe here is that well, you can always try to make this change in measure, but you only do this if the profiler really showed you that this might be an issue. If you see a big number of branch mispredict, and then the profiler told you that this is the line that contributed to those branch misprediction, only then you go and try to make the changes.
This is related to the slide before of this one. Can you explain that graph on the right-hand side?
Oh, on the right hand side.
Yeah.
Oh, it's actually just a sort of a visualization of those numbers. So I think the graph tries to emulate the pipeline. Sort of if the path was mispredicted, it sort of goes somewhere, I don't know, somewhere. If it goes in the right direction, so eventually all the instructions will be retired, right? So this is sort of how your instructions progress through the pipeline and what is the band in this pipeline. Yes. Yeah.
When is Intel going to make VTune affordable?
Yeah. So the question is when Intel will make VTune affordable.
Not that I didn't
It's
say
affordable.
free. I don't mind paying for it, but I think that the current price structure for VTune and the entire studio package is really unfriendly to individuals and to small companies.
And also the big companies.
I'm not.
I mean, take this back to campus and ask Steve Karumpas what he's going to do about that, okay?
Okay, so I mean, my take on this, I'm not, really qualified to answer, but I actually think you can have a 1 year sort of a trial license. It was, I think it was extended to 1 year, but I'm not sure.
Not VTune.
If you are a big company.
It does it on the other tools.
Oh, the no
VTunes is excluded.
Oh, I see.
I tried.
I have an input. I mean, I tried it 3-4 months ago. Just putting an email address.
I know
sufficient
that
to bring
you
it
can get a free trial for 1 month. You can get one for Windows and one for Linux. And then, if you have multiple email addresses, as some people do, then you can get another trial using a different email address. But eventually, you run out of options on this stuff.
Are there any other questions?
I think from a competitive perspective, I think it will actually benefit Intel a great deal to make this tool more available and more affordable. Especially now that you have AMD chasing your tails and
We can talk about this offline. Yes.
If you want your code to run well on a CPU with less cache than the CPU you're using, is there any way to sort of tell your CPU not to use all of its cache or some other technique to accomplish the same thing as that?
Yeah, how do you cross-platform profile for some other system?
Oh, okay. So there are two questions simultaneously. So the first question is how to limit the cache sort of a footprint. I'm actually not sure how to do this, and I'm not sure if you are able to do this at all.
What was the question, by the way?
If you're willing to take a huge speed hit, you can actually do this in software in cache grid. Because cache grid, it's part of the Valgrind suite, and it will emulate in software whatever cache architecture you desire. It's really slow. Valgrind, V-A-L-G-R-I-N-D. It's a software-based profiler. It's slow, but it gives you really good data.
So the observation was that you can use cache grind or Valgrind and emulate your cache hierarchy in software. I think there
And then the other one
was
was, do you have any thoughts about how to profile for, say, let's say I'm developing, I've got my code on the Mac or on Intel, but I'm going to be targeting, say, an ARM platform. Are there any sort of techniques, or is this really, now we're starting to get off the deep end?
This is probably so I tend to think that profiles are not portable. I mean, yeah, you probably shouldn't be doing this.
Richard, let's take that offline. I have an answer for you, but it is not a politically correct answer. So I will keep that private.
Will these tools work in a virtual machine, or do you have to run an operating system?
Yeah, good question. So will those tools work if you run it in a virtualized environment? And actually, so the answer is usually no. So because you don't have access actually to the performance counters inside virtual machines. So it's difficult. I would say. I think that it's possible, but it's difficult. So it doesn't work out of the box. Yes.
It depends on your virtual machine. VMware has an option for accessing the performance counters. So VMware, yes. I'm not sure about the free one. VirtualBox. I don't use that one.
Okay. I'm an opposite.
Yeah, it's in the options. Go to settings, you'll see performance until performance counters.
Oh, okay. Okay. So the comment was that it depends on a virtual manager. VMware supports and sort of exposes the performance counters for virtual machines.
As far as I know, and this information is maybe a little stale, VMware, the VMware hypervisor, is the only one in the market that actually exports, virtualizes all the performance counters. Everybody else is cheating. It took, if you read Brendan Gregg's blog, it took Netflix 2 or 3 years to convince Amazon to expose more performance counters in AWS. One of the most annoying things, and same story with GCP and whatever, they will tell you, the standard explanation as to why they don't do that is that it might become a security issue and it might allow clever system programmers to figure out where their software is running and blah, blah, blah. There may be other explanations to why they don't want to do it. In particular, one of the counters that all the major cloud operators have blocked, that are not virtualized and not exported, is the temperature sensor. And you can figure out how they did that.
So are there any more features in VTune that Perf doesn't have? Like, why would you use VTune if Perf has compatibility with all the microarchitecture?
Mm-hmm. So the question is, can Perf do all the things VTune can? And I think to the large extent the answer is yes. So Perf is capable of doing almost all the things that VTune can. Some of the features that are new, they have sort of a limited support and don't work quite well. Like, for example, processor traces. You can dance still. You should dance first a little bit just to make it work. But the killer feature of VTune is of course it's GUI, so the graphical sort of representation. So Perf doesn't have this.
But Perf does not provide all the analysis that VTune provides, and that's the high value. The high value is not just reading the counters and tabulating them.
Well, it does.
Will Perf work on AMD?
And Perf work on AMD, yes.
Well, that's a different issue.
Well, yeah.
It's a different dimension of the same issue.
Actually, provide that grid space in UI, so you can actually have that your source code. It's Perf. Like Perf report, they provide the text space in UI. But it's really nice. You can see the you can zoom into your source code.
Yeah.
To see the hotspot.
Yeah. So some prefer actually the text-based sort of output. that perf provides.
Does VTune work with WSL, the Windows subsystem for Linux?
So the question is, does VTune work for WSL, some sort of a Linux environment inside Windows? I'm not sure, and I can't answer this question. I don't know.
Well, on Linux, perf needs to match the kernel version, so I doubt that it works in WSL, where you don't put kernel.
When you were talking in the very beginning about setting up the benchmarking environment, you mentioned something about the dynamic scaling.
Yeah.
How do you disable that?
Well, there actually, I think there are multiple ways to do this. So you can do this in bias. So this will be like the sort of the true way to do this. You can also, if you have a root access, you can also do this from operating system, from Linux, for example. There is a special setting. I don't remember, but I have this in the link that I provided. Yeah.
I think it's the x86 energy perf stack utility.
Something like that.
And through BIOS you can disable Intel speed select or whichever option is there for turbo. That should be the one. That will set it to base frequency.
So are there some pathological cases where your thing gets front-end bound?
Okay, so the what is the example where when you get the front-end bound? So the front-end bound metrics means what it really means is that it actually attributes this time that was wasted when the CPU is capable of doing work, when execution units are free, but it doesn't have the instructions to work on. So this is the case. So example can be, for example, you are experiencing the instruction cache miss, right? So if let's say you are doing a long jump and you are jumping to some target that is not in your instruction cache, you are getting missed.
So that would not be memory bound?
I'm sorry?
That would not be the memory bound, because there's a memory bound as well there.
No, this will not be a memory bound. Yeah,
because the next instruction may be fetched from the L2 cache or the L3 cache. So, missing in the instruction cache doesn't mean you're memory bound.
Yeah. So when you miss an instruction cache, you are front-end bound.
Okay.
When you miss the data,
when you miss the data,
then you are in memory bound. Okay. Because remember, the load actually is executed sort of inside the pipeline. Okay. So you are the load is issued only after you are actually decoding the instruction itself, right? So then you issue the load.
Explain the machine clears by speculation.
All right, that's tough.
What's the question?
I'm actually I can't remember right now, so I will better not explain this. Yeah.
Does an equivalent of top-down methodology exist on something like ARM ISA or ARM CPU?
Yeah, I think so. So the last time I checked, AMD supports only the 4 high-level metrics.
Okay.
Return, front-end bound, best speculation, back-end bound. So you cannot really drill down deeper, but those four metrics are supported. And as far as ARM, I'm not sure.